All right, everyone. This is Valentine from Chemplistic again, and we are going to look at a reaction which is going to use an equation called the Arrhenius equation. Okay. So the problem out here says the reaction has a frequency factor A of 11.2 times 10 to the power 10 per second. It has an activation energy of 49 kilojoules per mole. And it's asking what is the rate constant for the reaction at 67 degrees Celsius. So anytime you see the terms frequency factor and activation energy, and they're asking for the rate constant, you want to think Arrhenius equation. All right. So I'm just going to go ahead and, on the right-hand side, write the Arrhenius equation. And the Arrhenius equation we're going to use, the form we're going to use is the logarithmic form. So we have ln of k, the rate constant, is equal to negative EA over R. And that whole thing is, times, we can just put the t with the R out here. So minus EA over RT plus ln of A, which is the frequency factor. Okay, so now let's list out what's given to us. We have the frequency factor A is given to us as 11.2 times 10 to the power 10 per second. We have the activation energy EA is equal to 49 kilojoules per mole. And we have the rate constant, we have the reaction temperature at 67 degrees Celsius. All right, so before we can apply everything into this equation, we have to understand what value of R we're going to use. So R is the ideal gas constant, and that is 8.314. This is what we're going to use, 8.314 joules per mole per Kelvin. And looking at the units of R, we have to decide what are the units of temperature we're going to use. So since R has a Kelvin in it, we have to change temperature to Kelvin. So that means we could add 273 to this, and that is going to give us 340 Kelvin. And then another thing we need to think about it, since R is given, we have joules in R, we have to convert kilojoules in activation energy to joules as well, which means we have to multiply the 49 with 1,000. So therefore, the activation energy we'll use is 49,000 joules per mole. And we can write this per mole as joules mole inverse. All right, so now we know what we're going to use. So I'm just going to go ahead and I'm going to highlight what we're going to use out here so that we're not confused about what to use. So that's the activation energy. My highlighter is too thick. Let me use a slightly thinner form. All right. All right. So that's the activation energy. That's the R we're going to use. That's the temperature that we're going to use. And that's the A, value of A. So let's plug that all into this equation. So we have ln of K is equal to minus 49,000 joules per mole. And the whole thing is over 8.314 joules per mole per Kelvin times 340 Kelvin plus ln of the activation factor, the frequency factor, which is 11.2 times 10 to the power 10. Second inverse. All right, so this entire thing, if you plug that into your calculator, you get negative 17.33 something. And I'm not going to write out the units right now. I'm not going to worry about them. And this entire thing becomes 25.44 and some more decimal places. Okay, so I add them together, I get 8.107. And then and that is equal to ln of K. So this is essentially the log, this value is equal to the log of K, okay? So to find what K is, we have to take the anti-log. And the anti-log would be K is equal to E raised to 8.10746, and this is equal to 3319.136, and continues. And if we have to round to the correct number of significant figures, we're going to stop here. So we're going to do we're going to make this 3, and we're going to drop everything else and add placeholder zeros. So that's 3,300 per second. And you can even write this in scientific notation. So that should be 3.3 times 10 to the power 3 per second. I hope that made sense. Thank you for watching.